Hi, I'm Danijar, and this is my talk on general Infomax agents through world models. The long-term vision here is to build a machine that replicates the functionality of the brain. Such a machine will be embodied in an environment and interact with it through sensory inputs and actions, so we call it an agent. But how can we build such a machine? One option would be to maximize survival, or the chance of survival, as the only objective function. But this would be computationally very expensive. And even if we could come up with an intelligent agent that way, it may offer limited insights on the computational concepts within the agent that allow it to be intelligent. Another approach would be traditional reinforcement learning with a manual reward function. But how can we design a reward function for a complex environment like the real world that will lead to interesting behaviors? And if it is a sparse reward function that will be easy to define, the agent will never get a reward by random chance, so the reward function alone will not be enough learning signal for the agent to learn anything, and the question becomes how to explore. So instead of these approaches, let's start from first principles. In this talk, I will propose that there is a spectrum of agent objectives, from narrow agents to general agents. In the artificial intelligence literature, many agents have been proposed. Some of them are more general than others. For example, there are agents that only optimize external task rewards. There are agents that also learn representations of their high-dimensional image inputs, for example, through autoencoders or contrastive losses. There are agents that learn world models of their environments that they can use to plan into the future. And there are agents that learn skills that can be reused for later tasks. So how can we organize this space of objective functions? I will propose that narrow agents are the ones that are driven purely by external task rewards. Task rewards are inherently subjective and domain-specific, and agents that only optimize those don't learn anything beyond what is needed for the specific task. On the other hand, there are more general agents that are driven by information maximization. This includes unsupervised objective functions such as representation learning, exploration, and empowerment. To maximize information, agents need to predict aspects of their trajectories, as we will see later on. This allows us to organize these objective functions based on how general they are, which corresponds to how much of their trajectories these agents can predict. And such agents learn and control as much as they can about the environment, so they can use task rewards, but they are not reliant on them, and they can be completely unsupervised as well. To understand the spectrum of agent objectives, we will start by looking at the space of all possible agents. Within that, we will see what characterizes general agents as opposed to narrow agents, and use this to derive a recipe for building general agents. We will then look at implementations of this recipe in practice. We describe agents by the random variables that they use to reason about the world and compute their actions. Random variables allow agents to represent uncertainty. This can help avoid overfitting from limited data. It can also help agents seek out uncertainty to explore the world, or to avoid uncertainty when safety is critical. Every agent has a lifetime trajectory distribution of these random variables. In the simplest case of stochastic control, that is just a very long sequence of sensory inputs and actions. But more sophisticated agents can use additional random variables, for example abstract options that guide the decision-making for multiple time steps. Random representations allow agents to incorporate information bottlenecks or uncertainty-aware state estimation. And Bayesian agents even use random variables to describe their parameters so they can model uncertainty in them. Let's look at some examples of trajectory distributions. Here we see the trajectory distribution of an agent that simply computes the next action from its current sensory input, and this action is then sent back to the environment. The dashed line shows the boundary between the agent and the environment. At the top we have the agent with all the variables that it can control. In this case, that includes only the sequence of all the actions, A1, A2, A3, and so forth. And so the set of all the agent variables along its whole lifetime is summarized by the letter Z. And below the dashed line, we have the environment. And this is the sequence of all sensory inputs, x1, x2, x3, until the end of the agent's lifetime. And the sequence is summarized by the letter X. Some of these variables have already been observed. In this case, x1 and x2 have been observed, and the first action, a1, has also been decided on already. So these are filled out. Here we see the trajectory distribution of an agent that uses stochastic representations, h1, h2, h3, to compute its actions. For example, these could be used to introduce an information bottleneck that limits the amount of information that the agent extracts from its inputs to help generalization. Or the representations could be learned as the codes of a variational autoencoder to help learn from high-dimensional inputs. In this example, the agent never commits to specific values for its representations. Instead, it treats h as a latent variable. The agent variables now contain the sequence of all actions and the sequence of all representations, where the actions will become observed over time, but the representations will never become observed. Another reason to use latent representations is to integrate information over time in partially observable environments to estimate the underlying state of the system. In this case, the representations h1, h2, h3 are not just computed from the current input, but also from the previous representation and previous action. This resembles the structure of, for example, a Kalman filter or a world model. So far, we've seen examples where the agent variables were aligned with the time steps of the environment, but this does not have to be the case. For example, in hierarchical reinforcement learning, we use options, G1, G2 in this picture, that condition a sequence of more than one low-level actions. In this case, the agent commits to its past options, so the options become observed over time, just like the actions. This last example of a trajectory distribution is that of a Bayesian agent that uses a random variable to represent uncertainty over its model parameters, for example of a world model or in this case of the policy. The global parameter vector W here is again never observed because it is treated as a latent variable. In general, we denote the trajectory distribution of an agent as P of x, z, where x is the lifetime trajectory of sensory inputs and z is the set of agent variables, some of which will become observed over time. The trajectory distribution is also parameterized by the current parameter vector phi, which determines how the agent computes its random variables from their inputs. We can now get a better idea of the space of possible agent objectives. For this, we think about the trajectories that the agent prefers, that we denote by the target distribution. We can formulate the agent objective as trying to bring its trajectory distribution towards such a target distribution tau. The target distribution, or simply target, is similar to a reward function, but it is more general because it's not only a function of each individual time step, but of the sequence of all time steps, so there can be dependencies, and it is also a function of the agent's internal variables and its actions. So by choosing different sets of agent variables and different target distributions, we can now implement many different agents. Let's see which target distributions correspond to general agents. Every agent has a target distribution, but which target distribution should we choose? Let's look at some examples. In variational inference, we're trying to minimize a KL divergence to bring a belief distribution or distribution over representations closer towards a probabilistic model. An example of this is a variational autoencoder that has a prior over codes tau of z and a decoder tau of x given z. The decoder leads to a reconstruction term in the objective. And we can see that the decoder connects the inputs and the internal variable z. As a result, they are dependent in the target distribution, and by minimizing the divergence, the two variables also become dependent in the belief distribution. This means we will infer beliefs that are informative of their inputs. As another example, there is reinforcement learning as inference, where we're trying to bring a trajectory distribution closer towards the trajectories that have higher rewards. The reward distribution here expresses the preferences, and we can see that it doesn't have any dependencies between the different inputs or agent variables such as actions or representations if there are any. As a result, the agent only tries to maximize its preferences, but it doesn't try to make its variables dependent. In contrast, it tries to have them as independent as possible. So in both cases, the target distribution expresses preferences, and writing them as KL minimization really shows that even in variational inference, the model is defining the preferences over what representations we want to infer. So from these two examples, we can see that the target distribution really combines two purposes. It expresses the agent's preferences over inputs and internal agent variables such as actions and representations. But at the same time, the target distribution is also the model architecture under which the agent infers its beliefs about the world, just like in the variational autoencoder example. Let's look at the dependencies between inputs and agent variables in the target distribution a bit more closely. Factorized targets, as shown here on the right, have the inputs and agent variables be independent of each other. Examples of these are preferences over inputs, such as task rewards, preferences over actions, such as an action prior, or preferences over representations. In trying to bring the trajectory distribution towards a factorized target, the agent effectively also tries to make the inputs and its own representations as independent as possible in the trajectory distribution. So it will extract as little information as necessary from the environment, and it will inject as little information as necessary back into the environment through its actions. The agent thus tries to realize its preferences or solve a given task while being as independent of the environment as possible. The agent performs information minimization, trying to actively avoid information that doesn't help in solving the current specific task, resulting in a domain-specific and narrow agent. On the other hand, there are coupled targets, as shown on the right, where the inputs and agent variables are dependent in the target distribution. Examples of these are probabilistic models that include an observation decoder, or a latent transition function, or a skill reverse predictor as used in option discovery. In trying to minimize the KL divergence to a coupled target, the agent will effectively also increase the correlations between inputs and its agent variables in the trajectory distribution. So with a highly coupled target, it will extract as much information from the environment as possible so that it learns a lot about the environment, and it will seek out informative future inputs and inject as much information back into the environment as it can. This results in an agent that, while realizing its preferences, also tries to learn as much as possible and become dependent with the environment. This agent maximizes information. It is an adaptive agent that adapts to new situations by absorbing information, and can be called a general agent that learns about many different situations. Agents with coupled targets maximize the mutual information between the sequence of their sensory inputs and the set of their agent variables. This explains a large range of different objective functions. We can see this by separating the mutual information into the mutual information between only the past inputs and agent variables, and the additional mutual information between the future inputs and agent variables given the past. So as we saw, an agent with a coupled target will extract as much information from the environment as possible. This leads to unsupervised representation learning that is guided through the past information maximization, making the representations become informative of past inputs. This accounts not just for representation learning, but also for model learning. So we're making no assumption about an environment model being available. Everything is being learned through this unified objective. For future time steps, the agent tries to maximize the mutual information between its latent representations and future inputs. This means it will seek out inputs that are informative of its current variables, known as the expected information gain, or Bayesian experimental design that leads to effective unsupervised exploration, where the agent tries to learn as much as possible about the environment by seeking out interesting situations. Moreover, the agent will try to maximize the mutual information between its actions and future inputs, leading to unsupervised control, where the agent tries to choose actions or temporally abstract options that have high influence over the future sensory inputs. For simple agent variables, the past Infomax and future Infomax terms lead to known objective functions in the literature. Stochastic actions don't have a past Infomax term because past actions are observed and past inputs are also observed, so their mutual information cannot change anymore. But the mutual information between future actions and future inputs is known as the realized empowerment or transfer entropy or controllability objectives, where the agent tries to choose actions that have a measurable impact on future observations. Temporally abstract options have the same situation for past time steps, so there is no past Infomax term. But for future time steps, they lead to skill discovery or option discovery algorithms, such as variational intrinsic control, diversity is all you need, and so on. Stochastic state representations are never observed because the agent treats them as latent variables. So for past time steps, they lead to state estimation, such as in a variational autoencoder or latent dynamics model. For future time steps, they lead to state exploration, where the agent is trying to open doors to see what's behind them and get a better idea of the current state of a partially observed environment. Model parameters for past time steps lead to system identification, where the agent tries to learn a model of the world. For future time steps, model parameters lead to model exploration, where the agent tries to reduce its uncertainty about the rules of the world by running experiments and moving objects around. And similarly, for policy parameters, past Infomax leads to inferring a posterior over policies, and future Infomax leads to exploration. We saw that divergence minimization is a unifying framework for comparing and combining agent objectives. Within that, factorized targets lead to task-specific narrow agents, whereas coupled targets lead to information-maximizing general agents. This suggests a path towards implementing general agents by designing more powerful world models. For example, we can capture more properties of human reasoning in the world models. In general, higher marginal likelihood leads to larger niches for the agent where it can understand its inputs, and the agent objective follows automatically. Specifically, given the world model, we should implement unsupervised representation learning, unsupervised expected information gain exploration, and realized empowerment. Let's now look at practical implementations that go towards implementing this recipe. Before looking at individual agents, let's first see whether human behavior can actually be explained through self-supervised objectives. For this, we evaluated 7 artificial agents across 4 complex environments and computed several unsupervised and supervised metrics from the lifetime trajectories, including input entropy, information gain, empowerment, task reward, and the overlap in inputs with human gamers taken from a demonstration dataset. We find that this measure of human similarity correlates more strongly with many of the intrinsic metrics than with task reward. Moreover, we find that all of these intrinsic metrics correlate more strongly with human similarity than they do with task reward. This offers some evidence that human behavior may be better explained through self-supervised objectives than through task rewards. To learn world models in complex environments, we designed the Planet agent. Planet learns a world model from high-dimensional pixel inputs using a recurrent state space model, or RSSM, that predicts forward using a compact latent space. This enables accurate video predictions and also enables thousands of parallel predictions during planning, enabling online planning with a large batch size without having to generate images. Across several continuous control tasks from pixel inputs, Planet resulted in a 200 times increased data efficiency compared to reinforcement learning agents without representation learning. Planning at every time step can be computationally expensive and often doesn't consider rewards beyond the planning horizon. Dreamer solves these problems by learning an actor and a critic in imagination using the world model. The critic is simply trained using temporal difference learning, whereas the actor maximizes outputs of the critic by backpropagating the predicted values through the differentiable world model. Dreamer exceeds model-free agents in terms of data efficiency, final performance, and computation time across 20 continuous control tasks from pixel inputs. The second version of this agent, Dreamer v2, is the first agent based on a world model to achieve human-level performance on the Atari benchmark. Dreamer v2 outperforms both previous model-based approaches and model-free approaches in the non-distributed setting. Moreover, the algorithm applies to continuous actions just as well and can control a humanoid to stand up and walk purely from pixels from a side view camera, as shown in this video. These improvements were made possible through 2 changes to the world model. First, changing the Gaussian representations to vectors of categoricals, and second, changing the objective through KL balancing to encourage more accurate prior predictions, resulting in accurate video predictions on Atari games for hundreds of time steps. Finally, Dreamer v2 performs just as well without using reward information for representation learning, suggesting that the world model really captures general information about the environment and can be useful for solving multiple tasks. Towards the goal of hierarchical planning with world models, we developed Clockwork variational autoencoders, a video prediction model that uses a hierarchy of latent state sequences to model video. This enables accurate long-term video predictions for 1000 frames across several datasets, outperforming all existing baselines. Moreover, the model has semantically interesting properties. For example, higher levels tend to represent content in the video that changes more slowly. And the level that ends up being used the most by the model is the one that corresponds the best to the frequency of the things moving in the video. So far, we've looked at examples of maximizing mutual information with the past to learn world models that can be used for planning. Plan to Explore maximizes also the mutual information with the future to collect interesting data. The goal here is to learn an accurate world model without any external supervision that is valid in as many parts of the environment as possible. and once learned, this world model can be used to solve many downstream tasks with no or little additional practice in the environment. Previous exploration methods usually work retrospectively. They seek out inputs that used to be surprising last time, but since the agent already saw them, they are not really novel anymore. Using an uncertainty-aware world model lets us perform forward-looking exploration instead, where we seek out unseen inputs that are expected to be surprising by computing the mutual information or expected information gain for different latent states. This expected information gain in practice is estimated as the ensemble disagreement of a transition model. Plan-to-Explore achieves the performance of supervised Dreamer on many of the 20 control tasks with no task-specific environment interaction. Latent skill planning maximizes mutual information with the future, not for exploration, but for skill discovery. The goal is to discover reusable skills inside of a world model to later on quickly solve new challenging tasks. Following the recipe, we maximize the mutual information between skills and the latent states of the world model that they end up in. For this, the actor gets conditioned on the skill, which changes every 15 steps, and is rewarded for reaching states from which the skill can be predicted well through a reverse predictor. The algorithm makes no assumption about 2D coordinates and works purely from pixels. After pre-training, we freeze the actor and select skills by online planning to solve downstream tasks. For example, here is a training environment of a quadruped with obstacles. After learning skills on this pre-training task, we can transfer to a downstream task where there is a wall between the quadruped and the goal at the end that gives a very sparse reward. Fine-tuning an actor trained on the training environment without any skills is hopeless in this case, because it doesn't explore at a temporally abstract enough level to get around the wall, whereas LSP has an easy time reusing its motion primitives to find the reward. To make tasks easier to specify for humans, Latent Explorer Achiever, or LEXA, learns to reach many goal images purely from pixels and without any supervision, not even goal images during training. For this, LEXA learns a world model to train two policies in imagination. The Explorer uses Plan-to-Explore to find interesting goals. The Achiever practices these goals using a learned temporal distance function in the latent space of the world model. After training, the Achiever can be used to reach user-specified goal images zero-shot without any additional training or practice in the environment. We introduce a benchmark of 44 goal images for unsupervised goal-conditioned reinforcement learning from pixels. Here we can see the Robo-Yoga benchmark, where the goal image and the agent behavior is shown. Moreover, LEXA can achieve challenging compound goals that require multiple actions to be performed. For example, on the right, we see a pick-and-place task where the robot has to move both blocks after another to achieve the goal image. In the complex kitchen environment, LEXA can perform goals or tasks that require 3 steps after another, such as moving the kettle, switching on the light, and opening the cabinet, all in one row. And finally, I would like to introduce you to the Crafter environment, a 2D procedurally generated world where the agent needs to explore a technology tree of different materials, tools, and skills, all while surviving by securing enough water and food and sleeping and defending against monsters. Previous reinforcement learning environments often only focus on individual challenges, but are too simplistic in other ways. To really test for general capabilities of agents, Crafter combines several different challenges into one environment, including generalization because of the procedurally generated terrain, exploration because of the deep technology tree, long-term credit assignment and reasoning because of balancing all the factors that are needed for survival, partial observability because of the local agent's view, and the non-trivial survival that can be interesting for unsupervised reinforcement learning. Agents on Crafter are evaluated by 22 achievements that can be unlocked in each episode. These can either serve as the supervised reward or as a metric to evaluate unsupervised agents. Here is an agent controlled by a human playing the Crafter game. As of today, the stable version of Crafter is released, and you can play it yourself by installing it on your computer using this command. I hope that Crafter will be a meaningful way to evaluate reinforcement learning agents going forward. With that, I would like to thank the audience and all my collaborators who have made this work possible. Thank you.